Welcome all to this opening colloquium of the second season of this Joint Mathematics Colloquia, joining University Autónoma Complutense SIC and Carlos III. And for me, it's really a great pleasure to introduce Stefaan Vaes. I will not say much about him. It's an outstanding lecturer, you will see, and researcher. Maybe for those of you that don't know him, he was invited speaker, the ICM in India 2010, fellow of the AMS, also a huge editorial work, editor-in-chief of Journal of Functional Analysis, I think memoirs and transactions, and many more. Mathematically, that's the reason we are here today. He is very much, he has several research areas and very much interested in the interaction between groups, ergodic theory, and Neumann algebras. And he will address today from this perspective, really hot topic in mathematics, which is the question about rigidity. And yeah, Stefan, he has visited also several times the ICMAT, and I'm very glad that you managed to come after pandemia, in inverted commas, again to ICMAT. So please, thank you very much.
Okay, thank you very much, Fernando, for the invitation, for the opportunity. It's great to be back in Madrid and to give this talk in front of a live audience. And indeed, I will be talking on von Neumann algebras, on operator algebras, and I will introduce this in at the, say, slow pace. So what is the topic about, first of all? So we are considering algebras of operators, meaning there is some Hilbert space around, and we look at star subalgebras of bounded operators on that Hilbert space. And these operator algebras, they typically come in two flavors. So the first flavor is really topological in nature. It makes use of the operator norm of an operator, defined like this. And with this operator norm, we can look at what is called technical problem. So we can look at the norm-closed subalgebras, star subalgebras of B of H. They are called C-star algebras. And then secondly, there is a weaker topology on bounded operators called the weak topology, where operators are said to converge weakly if they converge after applying it to a vector and taking a scalar product. And then von Neumann algebras is the second thing, are weakly closed star subalgebras of operators on a Hilbert space. Now, I will of course not touch to all kind of connections of this field with other areas. So there will be quite a bit of group theory in the talk today. There will be dynamical systems, mainly from an ergodic theory point of view. But there are very important connections and also very recent ones to quantum information theory that I will not address today. But maybe one of the most spectacular developments in operator algebras is, I would say, last 2 years on this interface. Some of you may have heard of the solution of the Kohn embedding problem, but I will not talk about that. But that's really a very intimate connection with quantum information theory. And representation theory, that is somehow one of the origins of operator algebras, where you would represent groups on a Hilbert space and try to learn something on that representation by looking at the C-star or von Neumann algebras generated by this group representation. Okay, so to give you an even vaguer but some flavor of what the difference is between C-star and von Neumann algebras and what kind of mathematics you may expect is, let me explain you which are the commutative operator algebras. So commutative operator algebras, when they are C-star algebras, they are precisely the algebras of continuous functions on a compact Hausdorff space. So up to isomorphism, that's what these algebras look like. And therefore, anything related to C-star algebras will have a flavor of algebraic topology, K-theory, continuous dynamical systems, geometric group theory. That's the kind of thing, keywords that you may hear around C-star algebras. On the other hand, commutative von Neumann algebras are precisely of the form bounded measurable functions on a standard probability space, and any probability space you encounter in your ordinary mathematical life is standard, so let's not go into that, are precisely of that form, and therefore you can somehow feel that anything related to von Neumann algebras will have a flavor of ergodic theory, measurable dynamical systems, measurable group theory. I will say something on measure equivalence and orbit equivalence at a certain point. So of course, we are not looking at commutative algebras. It's not the case that operator algebras is saying new things on these commutative cases. No, we are moving away from commutativity. And then probably the main source and first source of non-commutative operator algebras is coming exactly from group theory. So let's look at a discrete group where I will actually always assume that the group is countable and no further structure. So no topology, no, just a group. And then with that group, we get immediately several algebras. And the first one is straightforward. It's a so-called group algebra. And the group algebra, is there a problem?
Well, it does not seem to be emitting in YouTube.
Aha.
YouTube is just showing the
YouTube is stalled.
Yeah.
So then you want me to start again at a certain point, and then everybody can see whether I tell the same thing or or not. It would be an interesting exercise, actually.
So maybe should I go up?
Yeah, you can call from there, right?
And so now then,
Do we know the number?
707.
707.
Oh, now it's working. Okay. Now seems to be working.
707.
Well,
Okay, now it's working. Yeah,
but
sorry.
even on the, because that has still a warning. Your YouTube studio.
Yeah.
I mean, if I see on YouTube studio this big warning sign, probably something's wrong.
Something is wrong.
So, Mariano, or no?
Working
See.
need to be
It's just saying it's slow.
It says that the connection is slow.
Yeah. The bit rate is
Fernando,
inferior to the minimum recommended value.
Eh?
The bit rate is too low.
Well,
That's the literal translation of it.
And,
Why
and,
nothing's
fine.
and the machine is connected with the cable.
I believe so. Yeah,
Yes.
but it seems to be emitting.
It's a meeting.
Okay,
Please.
so we continue or?
Yeah, I think.
Yes.
okay,
Seems
so
to
no
be-
to worry. Mariano needs-
but
Yeah, I think.
I think it.
So what I was saying is that we are moving away, of course, from the commutative case, and then the first source comes with countable groups. So countable groups without any further topological structure. And the first algebra, still purely algebraic, that we associated to that is just the group algebra, which is nothing else than you take the vector space where the group elements are the basis elements, and then you multiply, well, as you multiply in the group, and you have already created a new structure, namely a star algebra, because you have the adjoint given by the inverse in the group. You create a star algebra just out of the group. Now that star algebra is naturally represented on a Hilbert space, namely little L2 of G, the square summable functions on the countable group G, by the so-called left regular representation. So you have these translation operators on L2 of G defining a unitary representation of the group, but also you can say linearize them. You can look at a linear span and define in that way C of G, the group algebra is represented on that Hilbert space. So you get already a star algebra of operators on a Hilbert space, but of course not closed in any way. And then you can first take the closure in this very strong norm topology, and that produces you a C-star algebra. It's called the reduced group C-star algebra. And secondly, you can take closure in a weaker topology, the weak topology in this case, and what you get is the group von Neumann algebra, already defined by Murray and von Neumann in the 1940s. And you can really view this as a chain of inclusions. So you have the group sitting as elements in the group algebra, invertible elements, unitary elements. This is sitting as a norm-dense subalgebra in the reduced C-star algebra, and then it's sitting as a weakly dense subalgebra in the group von Neumann algebra. And one of the basic messages here is that in principle, at each of these inclusions, some of the structure gets lost, some of the information gets lost. And one of the kind of rigidity questions we are interested in is, are there certain classes of groups for which actually no information gets lost, where this kind of weak isomorphism, say isomorphism of group algebras or isomorphism of C-star algebras, would actually imply groups to be isomorphic, for instance. That's the kind of weak isomorphism implying strong isomorphism question. Now, there are many, many open problems already on the group side. So let me start with the group side by quoting, I guess many of you are familiar with the Kaplansky conjectures. So take a group where every element has infinite order, so a torsion-free group. And a really wide open question is the unit conjecture. And the unit conjecture is predicting that the only elements that are invertible in that star algebra, that have an inverse, just as in algebra, are actually the non-zero multiples of these group elements that are inside and have their inverse, namely G inverse. This problem is extremely widely open in the sense that the classes of groups for which it has been proven is very, very small. It's basically only groups that have a certain order structure for which this can be proven. Now, there are variants of the conjecture. The idempotent conjecture is predicting that 0 and 1 are the only idempotents in that star algebra. And then, of course, a strictly stronger version of that conjecture is the Kadison-Kaplansky conjecture, saying that 0 and 1 are even the only idempotents in the reduced C-star algebra. Clearly, Kadison-Kaplansky implies the idempotent conjecture. That is trivial. There is also a relation between the idempotent conjecture and the unit conjecture, because, of course, with an unexpected idempotent, you can make invertible elements. If P is an idempotent, then I think 2P minus 1 is an invertible element in your algebra. So if the unit conjecture holds, then also the idempotent conjecture holds. I guess there is, again, a technical thing, maybe first to address, or...
It's just the camera, but I think the talk can go on.
Okay.
Yeah.
I'll try to. I'll try my best. So, very interesting to mention here is that this unit conjecture, if you do it over a finite field, because this group algebra, of course, we took the field of complex numbers because that's where operator algebras are going. But the group algebra makes sense over any field, of course. And there has been a recent counterexample to the idempotent conjecture over a finite field. But very ad hoc kind of counterexample. So probably it's not true in general, but to be seen. And then very, very interesting, although the idempotent conjecture is a purely algebraic statement on groups, the classes of groups for which it's known to hold is actually going through operator algebras. Because the classes for which we know it holds is because we know Kadison-Kaplansky holds, and we prove Kadison-Kaplansky because there is a connection with the so-called Banach-Tarski conjecture. And I will not go into that here, but we come later to the class of amenable groups. And for instance, for amenable groups, Kadison-Kaplansky is true because of Banach-Tarski being true. And therefore the idempotent conjecture is true. But I would not know how they could prove this without going through operator algebras, actually. Here, a very famous open problem now on the von Neumann algebra side. If you take a free group with a different number of generators, are their von Neumann algebras isomorphic? So this is the free group factor problem, has been wide open for many years. And then a bit away from free groups, people are very much interested in lattices in Lie groups. So take SLNZ, or here it's better to look at PSLNZ in this case, to divide by the center, which is at most of order 2. And the rigidity conjecture of Alankon is predicting, for instance, that the groups SLNZ have non-isomorphic group von Neumann algebras if the N and M are different. Why not 2? Well, for 2 it's known. If you take SL2 is very different from the higher rank SL3. So SL2Z is basically a free group, so they are not isomorphic to the other ones. But anyway, Alankon somehow made a much more bold statement that is then really what we would nowadays call a superrigidity statement. He is even making the bold statement that for any group having Kasdan's property T, for those who don't know the property, the SLNZ have this property. It's an abstract representation theoretic property of groups. Makes even the claim that for all groups with property T, the group von Neumann algebra remembers the group. So if L of G is isomorphic with any other L of gamma, this can only be because the groups are isomorphic, and the isomorphism essentially comes from this group isomorphism. It must be said, though, that I do not think that today Alankon would still make this conjecture, because back in the days, the source of property T groups were lattices in higher rank Lie groups. So I think the conjecture that might very well be true is that this is true for lattices in higher rank Lie groups, but there are these very wild hyperbolic property T groups. I think nobody believes that this is true in this very wild world. Okay, so already from these very simple examples, you can somehow feel that deciding on classification of operator algebras is a non-trivial task. So we have to put a bit more structure to go into that story. Yeah? So I have to give you a few basic definitions. So we already said that von Neumann algebras are these weakly closed star subalgebras of operators. And then there is the famous Bi-Combatant theorem of Murray and von Neumann. It's another characterization of what a von Neumann algebra is. So one way to construct von Neumann algebras is by looking at the set of operators T that commute with a certain set of operators S. The commutant will always be a von Neumann algebra. Von Neumann algebra is denoted with this prime, and prime is the commutant. And of course, everything in M commutes with everything in M prime. So M is always contained in M double prime. And one way to characterize von Neumann algebras is by saying that M is equal to its bicommutant. So the topological condition of being weakly closed is actually equivalent to this algebraic condition of being equal to the bicommutant. Then Murray and von Neumann, as we will see today, introduced some bad terminology. Factors is one of them, I would say. So a factor is really a simple object in the theory, which is kind of contradictory terminology, because von Neumann algebras, they have lots and lots of idempotents. So the simple objects are those that are not a direct sum of two. And that's really equivalent with saying that the center as an algebra, so really the center as an algebra is reduced to the multiples of one. So these are basic building blocks, that's clear. Everything can somehow be decomposed into factors. And then factors come in different types, which I will not define. I will tell you that all bounded operators are factors of type 1. But then important for us is that there are a special class of factors that have a state that has the trace property. These are the so-called 2-1 factors. And these 2-1 factors, they are really the basic building blocks of arbitrary von Neumann algebras. So there is the very involved Tomita, Takazaki, Kohn modular theory for von Neumann algebras that somehow gives you a process to construct any von Neumann algebra out of 2-1 factors. This is a bit exaggerated, but you should really consider the questions as first being important for 2-1 factors. Now, for our examples, this is not a problem, because we are now familiar a little bit with group von Neumann algebras. Now, these group von Neumann algebras, they always have a nice trace. Namely, we have a favorite vector in little L2 of G, then being 1 on the neutral element and 0 elsewhere. And that functional defines you a trace on the group von Neumann algebra. And we can also easily decide when the group von Neumann algebra is a factor. So a factor means that the algebraic center should be trivial. So the group should be far from abelian. And the correct condition is to be far from abelian in the sense of having infinite conjugacy classes. So if I take a non-neutral element, its conjugacy class should be an infinite set. And that is abbreviated as ICC, infinite conjugacy classes. So what's the takeaway here? For any countable group with infinite conjugacy classes, you get this 2-1 factor L of G. This trace can be evaluated on projections. And if you evaluate the trace on a projection, you get a number between 0 and 1. Now, contrary to the normalized trace on n by n matrices, where of course the possible values is quantized, the projection gets as value of the trace a multiple of 1 over n, if it's in n by n matrices. Here, in a 2-1 factor, the trace can take any real value between 0 and 1 on a on a projection. Okay, so that's the context of 2-1 factors. And let me now go right away to say a first big group of results that goes all the way back to Murray and von Neumann. So there will be somehow 3 families of results, the oldest one being from the 1940s. So Murray and von Neumann, they looked at so-called approximately finite dimensional von Neumann algebras. So what is a finite dimensional algebra? We know what it is. And we say that M is approximately finite dimensional if you find inside M an increasing sequence of finite dimensional subalgebras with the union being weakly dense. So if you can do that, then we say that it's AFD. And there is a very canonical construction. For instance, you could start by 2x2 matrices. You can take tensor products if you prefer, but you can also do it. You put 2x2 into 4x4 by just putting the 2 blocks like this, and then you put 4x4 in 8x8 by doing the same thing. You inductively continue, and there is a natural completion because you have to complete, of course, to get the von Neumann algebra. And that natural completion is what Murray and von Neumann called the hyperfinite 2-1 factor. Now, why the hyperfinite? Because, and this is really the first non-trivial isomorphism theorem in the theory, because they proved that all approximately finite dimensional, so here hyperfinite should be, it would be better to say AFD, all approximately finite dimensional 2-1 factors, they are all isomorphic. So that is a first, like non-trivial result, because if you would not take the completion, if you think for a minute, you could start with the 2x2 matrices into 4x4 into 8x8, but you could also start with 3x3 and then 2 times 3 every time, yeah, into 9x9, into 27x27. If you just think of that as a star algebra, you will immediately realize that they are not isomorphic because somehow projections can be divided by 3 a lot of times in one of these algebras and only divided by 2 in the other. The isomorphism really occurs on the analytic level after taking the weak closure. And actually, the isomorphism is not even occurring on the topological level. If you take norm closures, they are non-isomorphic, these algebras. And of course, you could vary the integers as you wish, yeah, 2x2 times 4x4 times 5x5. Each time you get the same limit object, which is the hyperfinite 2-1 factor. And the hyperfinite 2-1 factor is really everywhere around, because what Murray and von Neumann could also prove is that in any 2-1 factor are sitting incredibly many copies everywhere around of this hyperfinite 2-1 factor. They even speculate, and they could not refute this, but in a bit later today we will see that this is not true. They even speculated in their paper that the possibility exists that any factor in the case 2-1, that's how they called a 2-1 factor, is isomorphic to a subring of any other such factor. So they even speculated that this could be true, like the converse of this kind of amenability, which is not at all the case. But actually, even in their paper, they could only come up with 3 2-1 factors that they could prove to be non-isomorphic. So it's, and certainly they had no clue for this kind of thing. So that's the first isomorphism theorem. Now, in order to go to the second big group of results, we move all the way to the end of the 1970s, where Alankon did this great work on amenable von Neumann algebras. But then I first have to make a digression to groups again, and again go to group algebras, and say a few words on amenability for groups. So for me, the groups here, again, no topology. I mean, no further structure than just being a group. And then a group is said to be amenable if you can find a finitely additive probability measure on the subsets of the group that is translation invariant. So to any subset of the group, you assign a weight, say, a measure between 0 and 1, only finitely additive, and you need it to be translation invariant. Now, that's something that is rarely explicit. Of course, when G is a finite group, you just count the number of elements and you divide by the order of the group. Yeah. But when G is infinite, it's actually never explicit. And think a minute of Z. So you should somehow define what is the relative density of an arbitrary subset of the integers. Now, you cannot do that with a formula or an explicit way, but what you can do is to do it in an approximate way. You can count how many elements a set has between minus n and then divide by 2n plus 1. That's not translation invariant, but when n grows, it's almost translation invariant, and then some limit point, and there is some compactness argument, proves that m exists. Yeah. And the approximations are explicit. Now, these amenable groups, they were actually also introduced by von Neumann. So the concept is due to John von Neumann, and he introduced this to give a better explanation, a more conceptual one, to the Banach-Tarski paradox that many of you may have heard of, and the work of Tarski on paradoxical decompositions of non-amenable groups. So what Banach and Tarski were proving is that you can partition the solid unit ball into 5 subsets, and then you rotate and translate these subsets, and what you make out of that is 2 solid balls of radius 1, which sounds absurd, but which is not, because essentially it is saying that the group of motions of the 3-dimensional space is a non-amenable group. There is no way to measure any subset of R3 in a way that's translation and rotation invariant, because then you would have a perfect contradiction with your 1 and 2 balls. But simply, it's saying that such a way to assign a way to all subset does not exist. That's the only thing it's saying. By the way, Tarski also proved that in 2 dimensions, this is not the case. In 2 dimensions, there is no paradoxical decomposition of the disk. You cannot cut the disk infinitely many pieces, move them around, and get 2 disks of the same radius. And there, the reason behind is that this group of motions of R2 is an amenable group. So there is here a kind of phase transition, and you get already enough information on amenability by just looking at this, and then you see that the group of motions of R2 is amenable. So what kind of groups are amenable? The only ones that are trivially amenable are the finite groups. The abelian groups is not very hard to do some fixed point argument to prove that indeed there exists an invariant mean. And then amenability is stable under all kinds of constructions. It passes to subgroups, passes to direct limits. It's stable under extensions. So now you can start building lots and lots of new amenable groups. Those you can reach in that way, say, even after infinitely many procedures, would be called elementarily amenable. There are others. So that does not reach all amenable groups, but many. The prototype example of a group that's not amenable is the free group. So the free group F2 is not amenable. It has this paradoxical decomposition. And since amenability passes to subgroups, any group containing a free group is also non-amenable. And von Neumann and Day posed as a problem whether these are all non-amenable groups. Can you find in any non-amenable group 2 elements that have no relation among the 2 of them? That became known as the von Neumann-Day problem, which has a negative answer. So there are weird non-amenable groups that do not contain F2. Yeah? So there is this whole gray zone. And here is the most famous one that is really sitting in the gray zone. So the so-called Thompson Group. It's a single example of a group. It's a group of homeomorphisms of the interval 0, 1. Now, a homeomorphism of the interval 0, 1 you can draw by drawing the graph of the function. Yeah, it's just a bijection from 0, 1 to 0, 1. And now I look at the following countable set of bijections of the interval 0, 1. The graph has all these kind of linear things. The cutting points are all at dyadic rationals, like 1/4 and 3/8. So there are only countably many allowed cutting points, and the slopes are powers of 2, positive or negative powers of 2. So only countably many allowed slopes. So I have a nice countable group. That arises in other contexts as well. It's a group that comes with its action on the interval 0, 1. And the big open question here is this an amenable group? This is really the closest you can get sitting in between somehow. And there has been a period where basically every other year there would be a paper on archive proving that it's amenable, then the year after it would prove that it's non-amenable, and then this has continued in several actually editions, and now I think it's generally agreed that it's wide open. But there have been a lot of attempts. Okay, so why am I telling you this about amenability? Well, to introduce somehow the second group of classification theorems, of isomorphism theorems due to Alankon, because amenability is actually also a property of von Neumann algebras. And so here is just again the definition of an amenable group. But let me phrase the definition slightly differently in already a bit of an operator algebra flavor. A finitely additive probability measure on G I can also view as a state, as a positive functional on L infinity of G and G invariant. So equivalently, a group is amenable if there exists such a G invariant state on L infinity of G. That property has a natural von Neumann algebra counterpart, not too literally, but somehow. So Akeda Tomiyama, we are now in the 1960s, they gave an intrinsic definition of amenability for a von Neumann algebra, saying that an algebra of operators on a Hilbert space H is amenable if there is a so-called conditional expectation. It's a linear map, a projection from B of H onto M. And this somehow plays the role of this invariant state. In any case, it works well because the group von Neumann algebra is amenable in that abstract sense, even only if G is amenable as a group. So the concept is a good one. And then comes the famous theorem of Alankon. It's a half of his Field's medal. The other half will be on the next slide. Namely, he proves that every amenable von Neumann algebra is always approximately finite dimensional. And then if you couple this with the Murray von Neumann theorem, it says that all amenable to one factors are isomorphic with this single hyperfinite to one factor. So in particular, for every amenable group with infinite conjugacy classes, the group von Neumann algebra is always one and the same thing. It's always this single hyperfinite to one factor. Although if I give you two amenable groups, you will not be able to write an isomorphism between their group von Neumann algebras. You cannot get it explicitly, typically. Okay, so this is then, of course, for the 2-1 case, while the statement here is really for arbitrary von Neumann algebras. So, of course, they then want the full classification of all amenable factors. So factors because we have to somehow decompose into direct sums or direct integrals as unavoidable. And Alankon did manage to actually give such a full classification. And I will not go into type 3 factors any further than this. So in a minute you will forget. But the key thing is that Kon and Takazaki managed to find an invariant for arbitrary factors, an invariant that is an object in ergodic theory. The invariant they found is a flow. So they associate to any factor n a measure space and an action of the real line on that measure space that is ergodic. It comes as an invariant, as an isomorphism invariant. Now, ergodic actions, they can have 3 different forms. Ergodic actions of the real line, they could be the action on one point. That's not very spectacular. They could be periodic. It's still not very spectacular. These are the transitive ones. They could be, which is not listed here, are acting on itself by translation. And then you have all the others that are the so-called properly ergodic actions where every orbit has measure 0. So these are really the ergodic flows, if you wish. All the others are somehow the degenerate cases. Well, why is R acting on R not in the list? Because R acting on R, you get as a flow precisely for 2-1 and 2 infinity factors. So type 3 factors have one of these 3 flows that gives a further subclassification, and then a huge theorem completely concluding classification of amenable factors, namely, for each of the types except 3-0, there is each time a unique up to isomorphism amenable factor of that type. In 3-0, they are exactly classified by this properly ergodic flow. And the 3-1 case, which I already mentioned, but which is actually due to Hoover-Heuerup, is the uniqueness of the hyperfinite or amenable type 3-1 factor. And this then somehow concludes the story of, if you wish, of amenable factors. They are fully classified, of course, in terms of, if you wish, of something unclassifiable. I mean, there is a wild world of ergodic flows, but that's another story. Okay, so let's now move to the third era. Now we come much more closer to today, when like now 15, 20 years ago, Sorin Popa introduced this, what we call nowadays, deformation rigidity theory. And that has led to really remarkable rigidity and classification theorems for non-amenable factors. So here again, I recall you that when groups are amenable, they always give you the same von Neumann algebra. And here is now an example, now already from more than 10 years ago, of the completely opposite phenomenon. There are groups that are indeed having this superrigidity property that I mentioned at the start, namely there are countable groups for which the group von Neumann algebra entirely remembers the group. So it means that if you take any other group with the same group von Neumann algebra, the groups must be isomorphic. So these are groups that Adrian Ioana, Sorin Popa, and myself found back then. They are of a special form. I will not really explain this in detail, but let me nevertheless say a few words. So these groups are of a special form. They are so-called generalized read products. That's the technical word. So they are built as semi-direct product groups. So you start with a group with two elements, and then you take an infinite direct sum of the group with two elements indexed by a set I. And whenever a group gamma is acting on I, you can permute these indices. And what you get is an action of gamma by automorphisms of this abelian group. And the semi-direct product has a lot of very specific properties that are somehow related to Bernoulli actions and are therefore very much fitting into Sorin Popa's deformation rigidity theory. Now you notice here that I'm not giving explicit examples because they're a bit involved, but here are very explicit examples of superrigid groups. You can actually take as an action a direct product of two copies of the same group acting by left and right translation on gamma. And that will give you for many, many groups gamma, like the free groups, like free product groups, always give you such superrigidity phenomenon. So let me remind you that there is this rigidity conjecture of Alankon. The rigidity conjecture is saying that actually every property T group satisfies this conclusion. This is wide open, totally open. The only thing is that very recently, like less than a year ago, Adrian Ioana, Stefaan, and a few collaborators, they came up with the first specific class of property T groups satisfying this same superrigidity phenomenon, but still somehow an ad hoc class of property T groups, not like SLNZ or any nice property T groups, where this would, if you could prove this conclusion for SLNZ, that would be pretty spectacular. Okay, so far, basically all our examples of von Neumann algebras were a group von Neumann algebras. Now, von Neumann algebras and C-star algebras, they also arise in a dynamical context, when you not just have the group, but you have a group acting somewhere. So for instance, in the topological setting, I would look at the countable group acting by homeomorphisms of some compact space. It could very well be a compact manifold. And there is a so-called cross-product C-star algebra. I will say a few words on that in a minute. And those who are the operator algebraists should bear with me that I chose a bit of a strange notation, but I think it's somehow speaking more. So out of such a dynamical system of a group acting on a compact Hausdorff space, we can construct the C-star algebra. And then very similarly, out of a countable group acting on a probability space, we can build a von Neumann algebra. And in both cases, the operator algebra should somehow reflect the group action. And it reflects the group action in the following way. So by definition, the operator algebras contain the functions on the space X, continuous functions in the C-star case, bounded measurable functions in the von Neumann case. So these are sitting as subalgebras in your cross product. They still contain the group in the same way as group von Neumann algebras contained the group as unitary elements UG, lambda G they were on an earlier slide. And then the two together, they somehow encode how the group is acting on the space. So if you take the conjugation in that algebra of a function with such a unitary, what you get is the translated function. So the new function translated by the group action. Now, this is really very well amenable to all kind of rigidity statements. And let me now give you a similar kind of superrigidity statement, again in this context of Sorin Popa's deformation rigidity theory, where Sorin has done really a lot of work on specific group actions, a kind of canonical family of group actions called Bernoulli actions. So given any group G, countable, and given any probability space X0, you can look at this infinite product probability space on which you can act, say, by translating the infinite product factors. That's a nice ergodic probability measure preserving action. You can make this cross product. It always gives you a 2-1 factor. And again, by the same theorem of Alankon, if you plug as an input an amenable group, you again, yet another realization of the same hyperfinite 2-1 factor. Yeah? Now, if you move away from amenability, very often you get the strongest possible form of rigidity. For many groups, and I will go in a minute into which groups, but for many groups G, their Bernoulli cross product entirely remembers the group and its action. Really meaning that if that 2-1 factor happens to be isomorphic to any other such cross product, for any other, and there are a few natural assumptions of a freeness of the action, ergodicity of the action, then the groups must be isomorphic and the actions must be isomorphic. There is only one way to decompose this factor in such a way. This applies, for instance, to all property T groups. It applies to all direct product groups that are non-amenable and that are non-trivially in a direct product, like F2 times Z, property T groups like SL and Z. You see much more natural classes of groups. It's much better understood. And for those who are somehow familiar with operator algebras, they will recognize even the link with these read product groups, because the group for Neumann algebra of a read product group, if on the normal abelian subgroup you do a Fourier transform, are actually such Bernoulli cross products. So these theorems came first and are actually part of that, this input in the proof of the theorems for group von Neumann algebras. Okay, so far for this illustration of superrigidity for these cross products. Let's now go back to the free groups. So this is, of course, this big question, yeah? Do the free groups have isomorphic or non-isomorphic von Neumann algebras? And what Sorin Popa and I proved is that when you, instead of group von Neumann algebras, look at their cross products by free actions, of course, important that the action is free. For free and ergodic probability measure preserving, that's the abbreviation, actions, then they are never isomorphic. And the way we prove this goes as follows, because this is a good excuse to introduce a few other objects. So what we really prove, but I will not go into that technical term, what we really prove is that these cross products with the free group, they always have a so-called unique Cartan subalgebra. So this cross product by definition contains L infinity of X bounded functions as a subalgebra. And that subalgebra has a property, and that is an example of what we call a Cartan subalgebra. These 2-1 factors, they have a unique such Cartan subalgebra up to unitary conjugacy. Anyway, I will not go deeper into that, except by telling you the conclusion of that uniqueness theorem that we prove is that if these cross products are abstractly isomorphic, by uniqueness of Cartan, you will also find an isomorphism that preserves Cartan. So that sends L infinity of X onto L infinity of Y. Now that is something more specific. If you have an isomorphism of these cross products preserving the function algebras, that does give you a map, an isomorphism between the probability spaces X and Y, and not just any isomorphism. No, we are now in the realm of measurable group theory. We get what is called an orbit equivalence. So what is an orbit equivalence of two group actions? It's a measurable bijection between the probability spaces, mapping almost everywhere orbits onto orbits. So that's somehow, it's a notion that sits in between isomorphism of actions. It can hold for non-isomorphic groups, and isomorphism of two unfactors. It's a notion a bit in between. Now, there is a theorem of Damiat-Gaboriau, quite famous theorem, showing that the so-called L2 Betti numbers of a group are actually preserved under orbit equivalence. And I will explain you on the next slide what L2 Betti numbers are. But for the free groups, they are n-1. And so this then gives the conclusion, because we have found an orbit equivalence and we can distinguish with first L2 Betti number. So I think it's good to say here a few words on L2 Betti numbers, because it's one of these other places where actually operator algebras are giving back to say other areas of mathematics. So these L2 invariants for groups, here are a few names, of course, start by Attia and then Chikr-Gromov, Wolfgang Lück, are numerical invariants for countable groups. And they are a kind of advanced, or how to say, other variant of the ordinary Betti numbers. So ordinary Betti numbers of a group would be the dimension of a end homology or end cohomology space of the group, but ordinary vector space dimension. Now here, we are considering infinite groups. We are looking at the Hilbert space L2 of G. That's a G module. G is acting by left translation. So there is a well-defined notion of cohomology and homology of the group with values in that G module. Now, of course, these vector spaces, they are typically infinite dimension, but they also turn out to be modules over the group von Neumann algebra. And thanks to this kind of idea of continuous dimension, there is a way to measure a dimension relative to L of G in a way that has all good properties of a dimension function that you may want to have, and that allow you, for instance, it will say that this Hilbert space has dimension n relative to L of G, and measuring the L of G dimension of cohomology spaces is what they call the end L2 Betti number, and that numerical invariant was shown by Gaboriau to be invariant under orbit equivalence. Now, why am I bringing this up? Because there are a conjecture and a dream attached to that. A conjecture made by many people at many moments is that this invariance under orbit equivalence is actually an invariance under von Neumann equivalence, if you wish. So the conjecture is that if you have two groups and any free ergodic and probability measure preserving actions, if the cross products are isomorphic, then actually the groups must have the same L2 Betti numbers. The idea to prove this would be actually to show a kind of to show it in a strange way, in the sense that once some of the Betti numbers is positive, we expect these factors to have a unique Cartan subalgebra. But that's and then of course the conclusion would follow from Gaboriau. And then the big dream, but nobody really dares to make any predictions there, is that maybe we should be able to define in one way or another L2 Betti numbers for two unfactors. And then we should be able to prove, if the theory works well, that the first L2 Betti number of the free group factor L of Fn is n-1. But that is very far from anything that has been realized. Okay, then maybe in the remaining 5 or 10 minutes, let me discuss one recent result that we obtained. And let me go back to this speculation of Murray and von Neumann. Murray and von Neumann were saying maybe any two-one factor can be realized can be embedded in any other 2-1 factor. So we use this notation if such an embedding exists. So if it's possible to realize n inside n. Now, so far, all things that I've been discussing were related to isomorphism problems. I give you families of 2-1 factors, and when are some of these isomorphic and when are they not? Now, and there's much less known there, I want to understand when is there enough room in a given 2-1 factor to embed another given one into it. Now, here is, of course, the negative answer to the Murray von Neumann speculation, already from the 1960s. Amenability is inherited by subalgebras. So, no room to embed L of F2 in the hyperfinite 2-1 factor. There are other qualitative properties that are inherited by subalgebras. So, the higher-up approximation property, if you don't know it, it's not a problem, but the free groups have it, and property T groups do not have it. But it's inherited by subalgebras, and therefore, the algebra of SL3Z, no room to embed it in L of F2. By the way, this higher-up approximation property also implies the Baum-Kohn conjecture, and also these groups have satisfied the idempotent conjecture, where I started at the very start of my talk. Yet another thing, there is a very, very nice and very subtle non-commutative harmonic analysis invariant due to Cowling and Heuerup, the Cowling-Heuerup constant, which is decreasing if you take a subalgebra, and therefore, in these very specific cases where it can be computed, if gamma n is a lattice in this hyperbolic rank 1 Lie group in SPN1, then if n is larger than n, there is no room to embed L of gamma n into L of gamma m. There have been certain attempts to develop way more subtle harmonic, non-commutative harmonic analysis invariants for the group von Neumann algebras of SLNZ with the hope to retrieve n. So I'm sure that Javier was also involved with that and can tell more about that than I can, but so far it has not proven the similar statement for SLNZ, but it could. I mean, this is this open problem. Is there enough? Is it impossible, which we believe, if n is larger than m, to embed SLNZ into SLNZ on the von Neumann algebra level? Now, also there was this von Neumann-Day problem. Recall, von Neumann and Day were asking, does every non-amenable group contain F2? It's not true. There are counterexamples. But I actually believe that the 2-1 factor version might be true. That the non-amenable 2-1 factor always contains L of F2. But again, that's a quite wide open question. And conversely, there is actually a conjectural statement to describe exactly the 2-1 factors that can be embedded into L of F2. They should only be the hyperfinite 2-1 factor and the so-called interpolated free group factors. That's an interesting phenomenon in 2-1 factor theory. Again, a continuous whatever thing. We are familiar with L of Fn, the von Neumann algebra of the free group with n generators, but actually there is an L of Ft, where t can be any real number larger than 1, and it behaves really like the number of generators somehow, with free products and with everything you would expect. It has the formulas that as if this is the number of generators. And these should be the only ones that exist in L of F2. Okay, so in general, it's extremely hard to say anything specific and precise on embeddings and embeddability of 2-1 factors, but let me nevertheless state a recent result that Sorin, Popa, and I obtained less than a year ago. So still in this kind of Bernoulli framework, except that we are now working with more abstract cross products, so now I'm probably losing many of you. But anyway, there is some initial data that is an amenable base algebra, could be very much finite dimensional, as we will see. You can take an infinite tensor product indexed by a free group and then cross product by left and right shift. And this is a very large class of 2-1 factors because you have this arbitrary input data. And we can decide exactly when there exists abstractly an embedding of one of these 2-1 factors in the other one. Namely, it happens even only if there is a measure preserving, a trace preserving embedding of the initial data. Now, this may not sound so surprising, but let me show you the consequences. So you cannot, it's already highly non-trivial if you do this with just the two-dimensional algebra. So if you do this with the two-dimensional algebra, c to the power 2, a trace on C2 is, of course, yeah, it's like a measure on a two-point set. It's just given by the weight of the atom. So A is a number between 0 and 1/2. That's the weight of the one, and 1 minus A, the weight of the other. And what you get out of that is a one-parameter family of 2 factors. And you can prove that none of them can be embedded in any of the other ones. And that's also a phenomenon that you can typically not come up with in any non-trivial way. That you can then play games. You could take as a base algebra or a base probability space a continuous interval from 0 to A with total Lebesgue measure A, and then you add a single atom with weight 1 minus A as a base in the construction. And what you get is a one-parameter family of 2 factors. And abstractly, you can embed MA into MB, even only if A is smaller or equal than B. So by construction, they are sitting in this continuous increasing way. So that's the constructive part. But then you prove that there are no other possibilities to abstractly embed. So that's the remarkable thing. And you can play further with another base algebra. And what you obtain then is 2 factors that can, all of them can be embedded into any of the other ones, but none of them are isomorphic. So all kind of wild phenomena start to appear by just looking at this very specific example. And I think my time is up, so I will leave it here. Thank you.
Okay, thank you very much, Stefan, for this talk. Is there any question? Mark,
Yeah, can you go back to your conjectures about the L2 numbers of the 2 factors?
Yes, that was just before. Yep, this one.
Can one go a little bit further and assume, if this big dream was true, that the conjecture above that holds also for the group for Neumann algebras itself, not with the cross products involved? So I mean
that, of course, that would be even bolder. That indeed you would define L2 numbers for 2 factors in such a way that it's really compatible with L of G for arbitrary countable groups. That would be even more amazing. But it's not excluded. There is certainly no counterexample.
That would
yeah.
And what about the other conjectures a little bit after this? Can you go?
No, probably not here. Or
Next.
yeah, there.
So maybe not this one. Is there something else?
No, because then we were on this one.
No. Okay, no. Then that was it. Yeah.
Okay, thank you.
Oh no, yeah, I remember this. So I didn't get in the last point. You mentioned that in L2 your conjecture was that only the hyperfinite 2 factors and the
Interpolated 3 group factors.
This means L of ft for t, not an integer?
Yes.
Exactly that. Right?
Yeah, exactly that. And they all do embed. So that's not the point.
Yeah, is that this is all.
That this is all. Yeah.
This was a result by Dijkema, maybe?
That they all embed is basically the issue is to construct them. So and they were constructed by Dijkema and Radulescu, and somehow also already by Voiculescu, because he related L of Fn to L of Fk by amplification. So he somehow introduced L of Ft for rational t.
More questions, remarks?
So in this example you were showing where you have the group of 2 elements to some infinite index and then a group Attinger. So it is really important to have a group of 2 elements, or you do this just for simplicity in order to?
It's not important in the sense that if you put a finite abelian group, what we get is a description of all groups with an isomorphic group for Neumann algebra. And the description is just that you can replace the finite abelian group by any other finite abelian group of the same order. And then by construction, the algebras are isomorphic. And so if there are 2 or 3 elements, then there is only one abelian group with that order, but otherwise you have this list, finite list that are then exactly the groups that have the same von Neumann algebra.
Okay. More questions? Maybe I have one. You introduced the notion of amenable for Neumann algebra using these conditional expectations, but in the beginning, amenability was kind of linked as a property opposed to having paradoxical decompositions. And do these amenable for Neumann algebras, or is there a notion of a paradoxical decomposition of a von Neumann algebra, which is kind of opposed to this Tomiyama notion of amenability? But when you leave the groups, that's way more general.
No, that's definitely the question makes sense. I think one could formulate a property, but I'm not aware of any even only if statement like Tarski's theorem saying that you would have non-amenability even only if there exists such a decomposition. There have been results on certain paradoxical decompositions related to more at the star algebra and the C-star algebra level, but yeah. I cannot exactly tell you how far this went into an even only if characterization.
Because in its origin, Neumann introduced this notion of a kind of prevention of having these. There should be some kind of operator algebraic thing that cannot be done with a medium of Neumann. Okay. Thank you. More questions, remarks? If not, let's thank.
I wanted to ask again about this lamplighter type construction.
Yes.
So if I understood correctly, I guess what you can really distinguish is the action of the, right? So the fact that you have these finite abelian groups on the bottom, you say, okay, that's not really important because there's only a finite list of finite abelian groups. So I guess what is really distinguishing or saying that you must be isomorphic to this is really the action of the group.
So I'm not sure I entirely understand, but I think I do. I can tell you the following. So the point is that indeed, by construction, all of these are, say, semi-direct products with an abelian normal subgroup.
Yeah.
And then its group for Neumann algebra by Fourier transform is the same as the cross product of this dual compact group on which then gamma is acting. And so you're right in the sense that once these actions are isomorphic or even just orbit equivalent, then the group for Neumann algebras are isomorphic. So you also do need a framework where you can already from that action, if that is what you were hinting to, retrieve the group. Yes.
So is what I am getting from what I heard is that, okay, so if we can use actions, then we can tell apart von Neumann algebras, but as soon as it's just, so this example of this big question of whether we can tell apart two free groups of different rank, we can tell them apart if we let them act on something, but not if we let them act on themselves.
Exactly, or on one point rather. Yeah. If they act on themselves, then the cross products are all B of H. But if they act on one point, you would have the trivial action would give you the group for Neumann algebra, and there we don't know anything. But if they act in an essentially free way, which is very much opposed to,
essentially free. That's
exactly,
the key.
that's the key word.
Thank you.
Okay, thank you. More questions? If not, let's thank the speaker again.